Okay, good. All right. So we start to talk about relativistic UFT. And we wanted to review relativity really, really quickly. So that we started with this idea that light, speed of light, is constant, is the same in all reference frames. So that tells us that this combination for the forward time has to be the same, again, in all reference frames. And that then told us immediately that you have to actually think about Lorentz transformation. Which looks something like this. And when you go to the limit where the speed, relative speed between two reference frames is much more than the speed of light, you can do a data expansion and reduce that to Galilean transformation. So that's how we know that it's connected to Newtonian mechanics in the limit of low velocities. We also worked out that energy of the relativistic particle is given by this formula, and then you can put energy and momentum together into a single object called 4-vector. And once you have 4-vector, you can always build Lorentz invariant by contracting indices, one upstairs and one downstairs. And downstairs index means you flip the sign of the spatial components. So time component doesn't change, but spatial component flips its sign. So with this definition, and if you sum over the indices, this is E over C squared minus P squared. So this minus sign is what comes out from this downstairs index. And you can easily check that this is actually m squared c squared. And mass is an intrinsic property of a particle. So this is indeed the same in all reference frames. So that's how we know how to build Lorentz invariance. So if we have two vectors, AU and GU, then if you build this combination, this is Lorentz invariant. It doesn't matter which one you put downstairs, which one you put upstairs, but it's always contracted between upstairs and downstairs. You never contract two upstairs indices, you never contract two downstairs indices. It's always this combination of one upstairs and one downstairs. And because physics is sloppy, you don't want to keep writing it down all the indices, so often we just write it A dot B. And this is a little misleading notation, as you can see, because you often use this dot for your normal three-dimensional vectors, like A vector dot B vector. But this dot has this extra sign in it, so time component squared minus spatial component squared. So A naught is a time component minus, A naught, B naught, minus spatial components A and B. So this notation is a little bit ambiguous, but this is what we often do. So you have to be careful about what's meant by dot when you actually see it. And we are even more sloppy than this, because when you square the two things together, like P mu, we often just write P squared. So again, this is just a sloppy notation, but this is the way we often write things. But the point here is that whenever you see a Lorentz index, which runs from 0, 1, 2, 3, 0, 1, 2, 3, you can build Lorentz invariance by summing over indices, one upstairs and one downstairs. So that's a general rule. And there are actually only one more way to build Lorentz invariance. If you have 4 of these, you can also put this combination using Davinci beta symbol. And which is defined by the following. This is +1, and this is totally antisymmetric. And if we have seen this one in the vector calculus, for example, when you write magnetic field as a curl of A, this is defined by BI being this, right? So this is a 3-dimensional Davinci beta symbol, but now we're living in 4-dimensional space-time. This is a 4-dimensional Davinci beta symbol. And again, if you lower and raise the indices, I can talk about this stuff. And raising 0 to upstairs 0 doesn't change sign. But raising lower 1 to upper 1 does change the sign. The same for 2, same for 3. So overall, I get minus sign 3 times. So this is -1. And this is where I often make mistakes in my algebra, because just having lower and upper indices give you different signs. But nonetheless, that's true. So there are only 2 ways you can build Lorentz invariance. One of them is this, and one of them is that. And this one works only when all A, B, C, D are different from each other, because if they're the same, anti-symmetry will make it identically 0. And so that.
Yeah. Yeah. Why doesn't anti-symmetrization work for different from 4? Why does it have to be 4?
Because if any one of them is the same, then I sum over A1, A2, 1, 2, but this totally antisymmetric. And so they cancel.
What if I use a 5 index like beta and 5 different vectors? Why does that
So then you have to live in 5 dimensions.
Or, okay, sure.
So this is totally antisymmetric for all indices in a given space time.
It's like a determinant, right?
Yeah, that's right, exactly, right. So there are only 2 ways to build Lorentz invariance, so this is an ingredient we're going to use to write down the action for Lorentz invariance. Any questions so far? Yes, Jackie?
Did you explain why the upper index forms give a negative sign?
Yeah. So maybe I should explain one more thing to answer this question. So what you do to change lower index and upper index relies on this 2-index object called metric tensor. Which is a very simple thing, just this. So this is meant to be 4-dimensional generalization of Kronecker delta. Delta ij, so again in 3-dimensional vector calculus, you can build rotationary invariant combinations. And this is scalar, so rotationary invariant. And you can view this as delta ij, ai bj, summed over indices, right? So the idea is that delta ij in 3-dimensional space is now generalized to this object in 4 dimensions. Which one you'd like to choose for the plus and minus is convention dependent, some books actually use opposite sign for this. And that's convention, so when you read a new book, you better be sure which convention the book uses. Sometimes this one is called mostly negative metric, mostly positive metric, and that's one name we can give to them. But different convention, you have to pick one, and then you keep using it throughout. I am using this convention in my class, so this is what the one we are going to use, not this one. But using this object, you can freely move the indices around. You can raise it, you can lower it, but whenever you do this, then you have to play the signs of the spatial components, x, y, z components. So that's the way we deal with these upper and lower components. And then I have to come back to Jackie's question. I forgot.
I think it's answered.
Okay, good. All right, any other questions? Good. And the next thing is to understand how derivatives work. So, space-time coordinates, CT, X, Y, Z, is also 4-vector, so they come together. That's why we form this combination dx mu, dx u. This is dct, dct. So this was in the Lorentz invariant proper time, and that's because they together form another 4-vector. So if space-time coordinate is a 4-vector, the derivatives with respect to it is also a 4-vector. And then, because this x mu, here I'm writing as an upper index mu, derivative with respect to it is an object with lower index, because it's downstairs. So when you take these derivatives, they transform also as a 4-vector, but you have to be sure that this is actually a lower index instead of upper index. And so you can build invariants, for example, and this is actually what we're going to do later today, I hope, is that whenever you have a field phi, you take derivatives, and this is supposed to transform as a 4-vector. Then you can contract indices like this to build Lorentz invariant, which again we slowly write del phi squared. And this is meant to be, this one is this derivative, 1 over c, time derivative phi dot. And raising the time index doesn't change the sign, so just square of this. But when you go to next one, del x phi, raising the index from here to there would change the sign now because of spatial index. And same for y. And z. So at the end of the day, this becomes this, right? So the time derivative comes together with 1 over c to make sure that this derivative has dimension of 1 over length. This really has dimension of 1 over length. They have the same dimension. Then summing over the spatial indices, you have to have this relative minus sign, complete the piece with the positive sign for the time component. So that's how you can start writing down Lagrangian action to making sure that everything is Lorentz invariant in your theory. Okay? Any questions about this? So far, so good?
I'm not sure I really understand why, when you take the derivative, it ends up being a lower index, but you're taking the derivative with respect to the upper index?
Ah, okay, so let's see. That's a good question. So let's see, how do I show this explicitly? So let's just focus on the t and x and forget about y and t for now. And so what we talked about is the t prime, x prime, transforms with this matrix from one reference frame to another. So the question is, what is dt prime and what is dx prime? So dt prime is del t and t prime. This is del x. It's the chain rule. Right? So if you take t prime derivative, you can take t derivative and dt and dt cancels, and this is t prime derivative, or you can use x derivative, dx cancels as a t prime derivative, and same here. So far so good? Okay? And then you need to understand this del t prime. And to compute this, I have to take the inverse transformation of this. So tx t prime x prime. To do this, I actually have to put minus sign over here, so that the product of two matrices become identity. Then I can work this out explicitly. dt d prime is gamma. dx dt prime is minus gamma beta. And I do the same thing here, gamma del x minus gamma beta del t, which means derivative transformed by the inverse matrix from the transformation of the coordinates. So this is why this is meant to be the lower index objects, because transformers are the inverse of the upper index objects, which are the space-time coordinates, and that's why derivatives defined this way transforms as a lower index object. Okay? Thank you for asking. Any other questions? Okay, so that's basically the review of special relativity. It's a crash course, so you finished 131 in 2 lectures. And now we have to think about how to make this a quantum theory. And obviously, first thing you will think about, before going to QFT, is quantum mechanics, right? Why can't you make quantum mechanics relativistic? And what you get told in 137 is that energy is an eigenvalue of a Newtonian operator, and you promote this to time derivative. Momentum is also promoted to spatial derivatives. So why can we do that? To write down Schrödinger equation for relativistic quantum mechanics. Then the first thing you might want to try is that you have wave function where this IH bar dt is supposed to be the Hamiltonian. We derived this Hamiltonian last time from the Lorentz invariant point particle conversion. And if you follow this rule, what do you find? is this one. But now we are staring at kind of nonsensical equation. What the heck is this? Square root of something with derivative operators inside. You can try to make sense of it if you define by the Taylor expansion. I don't remember all the coefficients. You can try to make sense of it this way, but we know this Taylor expansion has a finite radius of conversion where this object has to be less than this, which means you need to be in this regime for this Taylor expansion to converge. Convergence. So what that means is that you can never talk about auto-relativistic particle where the kinetic energy is much bigger than the rest energy of the particle. So trying to make sense out of this weird square root of differential operator in Taylor expansion does not extend all the way to auto-relativistic particles. So this fails. You can't describe relativistic particle using this kind of wave equation. Then you say, okay, if the square root is a problem, why don't we take the square of the both sides? And make this into wave equation. And then I can just work it out. Sorry, this is supposed to go to square. And you can think about this equation. Now, if you stare at this long enough, you notice that this is actually pretty good. Because this combination, del t squared minus spatial squared, can be written as derivative with upstay index, derivative with downstay index. Time component is 1 over c dt. 1 over c cancel the c squared. So this is del t squared, that is this one. But for the spatial components, we are supposed to flip the signs. So this is del x, del y, del z. This is minus del x, del y, del z. So they sum up to this nabla squared with the opposite sign. So that's this combination over here. And if I divide both sides with negative sign and h bar c and c squared, you find del mu psi plus m squared c squared over h bar squared psi. And indeed, this equation is Lorentz invariant because whatever indices there may be are all contracted between upstairs and downstairs. So this is actually one of such famous equations called the Klein-Gordon equation. And we often even further simplify this notation by writing this del mu by box. And the reason why this is a box is when you go back and think about Laplacian, with this usual definition. In this case, we use the symbol delta because this guy lives in three-dimensional space. You guys live in three-dimensional space, right? So that's why you need to have three corners, or the vertices And that's the meaning of this symbol for the Laplacian. So if you go to 4 dimensions, sum over all 4 indices, then you need to have 4 vertices, and that's the square. So this square symbol is meant to be the Laplacian in 4 dimensions, but it's defined with this one negative sign inside. You have to be careful about this. And the name for this box is called Davinci. Well, just the name, but this is a good way of remembering what this is supposed to mean. This is meant to be 4-dimensional version of the Laplacian. You sum over all derivatives squared or for all directions, but because you are supposed to sum with one upstairs and one downstairs, this box is meant to be a combination of time derivative squared minus 3-dimensional Laplacian. Okay, so that's easy to remember, I hope. So this is the Klein-Gordon equation. It is Lorentz invariant. It's a wave equation. Looks good. So we have a relativistic quantum mechanics. Okay?
Yeah, so we wanted the convergence to hold, which is...
You're talking about this stuff?
Yeah, and may I ask, so, because if what we are doing is we drop the terms after the expansion, the Taylor expansion after order.
I dropped the other terms because I didn't remember the coefficients of Taylor expansion. But the point here is that even if you add all of them, this series, if this infinite series, which does not converge, that's the idea of the radius of convergence, right? So, for example, if you just look at this function, 1 over 1 minus x, Taylor expansion of this is this geometric series that keeps going. And when x is like 0.1, then this is 1 plus 0.1, 0.01, 0.001. So that will sum up to 1.1111111. And that works because left-hand side is 1 over 0.9, which is 10.9. And that is indeed this. So they agree. But if you plug in, say, 2 into it, left-hand side is 1 over 1 minus 2, that's minus 1. For right-hand side is 1 plus 2 plus 4 plus 8 plus 16. You keep summing positive numbers, you will never get minus 1. So something is wrong. And what is wrong with this idea that this series, this infinite series, does not converge? Which makes sense, because if you start with 1, next one is 2, and you add 2, so that's 3. 3 plus 4 is 7. 7 plus 8 is 15. So you have a curve like this one. And if you keep adding more and more terms, it just hits infinity, and you don't get a sensible answer to this. So that is the idea of this, the radius of convergence. Namely that this infinite series, 1 plus x squared plus x cubed and so on, is a series that converges when x on a complex plane is inside this circle of radius 1. If x is inside this circle, this series converges, and this expansion makes sense. But if you're outside this circle, you'll find this nonsensical infinity, and this expansion doesn't make sense. So Taylor expansion has limited applicability. They have to be inside this radius. And this Taylor expansion I talked about for this strange derivative operator basically requires the c times p has to be inside mc squared. So as long as momentum is small enough, then Taylor expansion makes sense. Perhaps this infinite number derivative operators make sense, even though I don't want to deal with it, that looks horrible, but it might make sense mathematically. But once you're outside, which does happen for relativistic particles like muons created in 20 kilometer altitude reaching the ground, they are super relativistic, that's why there's time dilation. Those particles would live outside this radius of convergence, so this wave equation doesn't make sense.
Thank you.
Okay, any other questions about this? All right. Okay, so now we seem to have a perfectly sensible equation. What's wrong with that? So this is a good equation as far as its Lorentz invariance is concerned, but it does not admit probability interpretation of quantum mechanics. So in quantum mechanics, Schrödinger wave function is supposed to be a probability wave. Its absolute square is supposed to be probability density. And this is the total probability That's why we normalize it into 1. So that's what we do in quantum mechanics. So if you want to use this interpretation of what this wave function is, then you need to have a guarantee that total probability doesn't change. The conservation of probability. This is an essential requirement in quantum mechanics to understand the wave function as a probability wave. And this was guaranteed in Schrödinger equation because when you take ddt psi squared, ddt psi star psi, and time derivative acting on psi is minus I Hamiltonian acting on psi. Time derivative acting on psi dagger is minus I Hamiltonian dagger psi. And because Hamiltonian is a Hermitian operator, if you take dagger here, this minus I change to I, Hamiltonian remains the same, that cancels this one, sorry, I mean plus. So that's how this total probability was conserved. Namely that was due to the hermiticity of the Hamiltonian, and also due to the fact that this is the first order differential equation in time. Namely, once you specify psi everywhere at a given time t, then Schrödinger equation is actually deterministic because wave function at a later time is completely fixed by this time evolution operator acting on the initial condition. So initial condition you need to specify is the value of wave function everywhere at a given moment. Then the rest of the evolution is totally determined. That's what Schrödinger equation is telling you, right? So that's what you guys learned in 137. Now, we have this Klein-Gordon equation, which is second order in time derivative. Well, that sounds like an innocuous change, but that actually completely changes this idea. Because if you have the second order differential equation, then you have to specify not only psi at a given time slice, but also its time derivative. Because the second order differential equation. And that's something you know from Newtonian mechanics. Newtonian mechanics, F equal ma, is second order differential equation. And in order to determine how particles move, you have to specify initial position and initial velocity. You need to specify both to predict, for example, how a ball in your hand will fall down to reach the ground. So you need to specify both initial position and initial velocity because you're dealing with second order differential equation in time. Klein-Gordon equation is the same. Because it's a second order differential equation in time, you have to specify this function at a given time, at every position in space, but also its derivative at that moment, everywhere in space. You need two pieces of data to determine the rest of evolution in this deterministic equation of Klein-Gordon equation. You can also ask the question, does the Klein-Gordon equation allow for this conserved probability? Well, if you actually take this time derivative, all you get is this. But we just talked about the fact that psi dot is an independent initial condition from psi. So even for a given psi, psi dot can be arbitrary, and that's not necessarily zero. Can be positive, can be negative, and it's not guaranteed to be zero in general. What that means is that you can't define this conserved probability. Therefore, trying to understand this Klein-Gordon equation as the relativistic Schrödinger equation doesn't allow for this probability interpretation. So it fails as a quantum mechanics theory consistent with relativity. And this is actually a very general fact. The relativity relates energy and momentum in this way, and this was required from Lorentz invariance, so there's no way to change that one. And we got this dilemma that if you want to write wave equation with this one, you find differential operator that doesn't make sense. If you take the square of this, then there is no conserved probability. So, relativistic quantum mechanics fails. It doesn't exist. So Klein-Gordon equation was, okay, nice try, but it didn't work out as a theory of relativistic quantum mechanics. So that's why people had to do something different. And that, in the end, required us to go to QFT instead of quantum mechanics. So in the non-relativistic physics we talked about in the first half of this course, QFT in some sense was optional. It was useful because it could describe BEC superconductor and that kind of system which you couldn't do with quantum mechanics. It was useful because you could talk about processes of like the emission of a photon where number of particles change. It was useful because quantum statistical is built in. You don't have to impose symmetry or antisymmetry of the wave function. But you probably could have worked out quantum mechanical formulation for much of it. But in the case of relativity, simply the quantum mechanics doesn't work. Then QFT is now forced upon you. There's no way out. Once you go to relativity, once you want to implement Lorentz invariance, QFT becomes must. So what we do is instead of taking KleinGordon equation as a probability wave equation like the Schrödinger equation, you take this Klein-Gordon equation as an Euler-Lagrange equation of QFT instead of quantum mechanics. So we write down, again, Lagrangian for the field theory to make sure that that Lagrangian leads to the Klein-Gordon equation as its Euler-Lagrange equation. And once we have a Lagrangian of QFT, we know already how to quantize it and get the field, the Hilbert space. And we follow this process, and it turns out that everything makes sense if you do that. So that is what I'm going to discuss next. But anyway, any questions about this discussion here? So when you first hear about this, I think my reaction was, really? Isn't there anything better we can do? But no, we can't. Yes?
Is this also the method that Dirac used?
I can't hear you at all.
Was this also the method that Dirac used? Like,
Say again?
was this also the method that Dirac used to?
Oh yeah. So we will talk about Dirac equation later on. So he came up with one sort of last attempt to create relativistic quantum mechanics, and which also failed in the end for a different reason. And I will talk about that later. Okay? But I'd like to finish up discussion about Klein-Gordon equation today. Any other questions? Okay, so now we decided that we would like to take this Klein-Gordon equation as a field theory. And if you're doing a field theory, you have to come up with a Lagrangian, and that is actually pretty simple. So the Lagrangian is integral of space. Lagrangian integral of time is the action. 1 in 1 is the action is Lorentz invariant. And you have already seen an example of this for point particle. Action was mc squared d tau. And because tau is a proper time, that was Lorentz invariant. And from that, we could derive the energy is square root of c squared p squared plus m squared c to the 4th, and so on. And you're working on that for one problem right now. So what we want to make sure is that action is Lorentz invariant. In one term, that's clearly Lorentz invariant. So phi doesn't change under Lorentz transformation. Then phi negative phi doesn't. So this looks good. But obviously, we want to also have terms with derivatives. And without derivatives, the particle would never move. And that's not something we want. So obviously, we want to do something about the derivative of the field. But having gone through the discussion today, you can immediately tell what you're supposed to do. Right? Then this is Lorentz invariant, because I contracted lower and upper indices, and you verify that the lower index transforms with the inverse matrix, upper index transforms with the original matrix, they cancel, so this is Lorentz invariant. So it turns out that this is the action of free Klein-Gordon. Free in the sense that we are not introducing any interactions for it. And when you take variation with respect to phi dagger to derive the Euler-Lagrange equation, then variation of this is del phi dagger. And I should have put minus sign here for the layer consistency. Phi And when you take variation with phi dagger, I should do integration by parts, and that changes the sign. And that's the version that we talked about. And this is supposed to be 0. That's the variational principle of this action principle. So in the end, you find this equation. That's exactly the equation we want to get. So this is the right action for the purpose of reproducing the Klein-Gordon equation as its Euler-Lagrange equation. So now we have accomplished the first mission, namely that we want to regard the Klein-Gordon equation now as a field equation instead of quantum mechanical Schrodinger equation. In order to use this as a field theory, you need to have the Lagrangian that reproduces this wave equation or field equation. And here we go, we got it. Once you have the Lagrangian, then you know how to quantize it. That's the next thing you do. By identifying canonically conjugate momentum, which I write pi, for some historical reason I don't know. A time derivative is in here, together with time derivative there, with a plus sign, because both of them are time component. So if you take the derivative with respect to this, I get that one, and I forgot what was c squared. And I should also define canonically conjugate momentum for phi dagger. And we know already what you're supposed to do to set up the commutation relation and same for phi dagger. And phi's commute and pi's commute among themselves. So this is the canonical commutation relation we used over and over again, right? So this is what we need to build up our Hilbert space. So any questions so far? Yes?
What do we need as the function for the t? For
Sorry?
time? Because I think, for example, when we were dealing with the polarization, we gave a quantum delta for the different directions of polarization. Now the coordinates becomes a four-dimensional coordinates. Then why do we need a delta function for the t?
Yeah, that's an excellent question. So here, when we're dealing with the Klein-Gordon equation, and I didn't mention it, and that's why you're pointing it out to right now, which is great, that I assume that phi is a single component object. It's not four component object like vector potential. So in the electromagnetism, we have this vector potential, which also comes, now that we're using relativistic commutation, as a four vector. So scalar potential and a vector potential combine together to form a four vector. So this comes with the index mu. So this is actually a four component object. And once you have a four component object, because you have these components, you have to deal with some kind of vector, which turns into the polarization vector we talked about in electromagnetism. Here, I secretly assume that phi is a single component object because it came out from the Klein-Gordon equation where we were trying to do relativistic quantum mechanics. We failed on that one. But at least we are still sticking to the idea is that phi is just single component object. It doesn't have any index. That's why we don't have to deal with the polarization vector, at least for now.
Yes. But I was trying to ask why there is another delta term adding multiply over there. Yeah. It should there is something should be multiplied like delta t minus t prime, I think.
Delta t minus what?
He's
Can you write it? Oh, careful, careful.
I was gonna say, if we, the conical canonical.
Oh, yeah. So if you remember what we did with harmonic oscillator in quantum mechanics, we have the Lagrangian. And that defines the momentum. And we define canonical commutation relation. But in this case, this is actually an equal time commutation. And normally you don't talk about this because normally you're shooting a picture where operators don't depend on time. But if you're talking about time-dependent operators, then you are using Heisenberg representation, Heisenberg picture. In a Heisenberg picture, x and p change over time. So when you set up this commutation relation, you need to specify what time you are referring to. And you also know that in case of harmonic oscillator, P initially is initial momentum. That's when the pendulum has swung to one limit. And over time, it goes down like this. And at this point, now it's x. So P and x change among each other. So if you think about commutation relation at different times, at a particular time, P turns into purely x, and this is actually 0. And then becomes minus P, then it's minus IH bar. Then come back to 0 again. So this commutation relation also changes over time if you keep these two times separate from each other. So xp being IH bar is strictly a statement between x and p evaluated at equal times. When you try to evaluate commutation relation at different times, then it may not be IH bar in general. So when we actually write down canonical commutation relation, these are all equal time commutation relations, namely that t prime and t have to be the same. That's when we set up the commutation relation being IH bar. Because the time had to be already set equal, you don't put this delta function in. Because it's there by definition of an equal time commutation relation. And again, you don't talk about this much in quantum mechanics class because you kind of assume you are dealing with a Schrödinger picture. But in relativity, it's much more natural to talk about a Heisenberg picture because if field depends on x, you want to treat space and time on equal footing, so the field better depends also on time, so that you have this concept of space and time working together. But when you set up this canonical commutation relation, you have to evaluate it at the same time for both variables in canonically conjugate momentum, so that you can write this canonical commutation relation being just IH bar. Okay? Thank you for the question. Any other questions? Yes, Jackie?
So in any case, it wouldn't go as delta.
Say again?
If, I guess, what you're saying is that if you think about the harmonic oscillator example, if t does not equal to t prime, the commutator doesn't go to 0.
It goes to 0 at some
At
times.
some times.
Yeah.
So it wouldn't go to delta anyways.
Right, so what we know is that x of t is x of 0 cosine omega t plus p0 over m sine omega t. P of t is p of 0 cosine omega t minus x0, I guess m omega sine omega t. Is that right? Yeah. So this is and if you evaluate this at different times, the pieces that don't commute is this times that one, so IH bar cosine squared omega t, and also this and that one. And this is 0 and t, that's what I put here. No, I'm doing something wrong, sorry about that. x0 and pt. So I'm computing commutation relation between this one and x naught. This one commutes, this one doesn't. Yeah, this is the right one, sorry. So you see that when t is pi over 2 omega, then cosine omega t vanishes and they actually do commute. And this oscillates. Starts out with IH bar when t is 0, that's the canonical commutation relation, but then it starts to decrease and becomes 0 and come back over time back to IH bar. So this commutation relation will be fine if you don't take equal time commutation relation. Okay? Any other questions? Okay, so the process is exactly what we have done with shortening the field theory and also electromagnetism. Once you have this canonical commutation relation, you go ahead and write down the mode expansion in momentum space to identify creation and annihilation operators. And to get the coefficients correctly is a little bit of a trial and error, but I've done it already, so I just write down the answer to that. So if you're using box normalization, then if you use the usual commutation relations between creation and annihilation operators, but two sets of creation and annihilation operators, and everything else vanishes. So if you do this mode expansion for phi dot, and also phi dag and phi dagger dot, which is just the Hermitian conjugates of these, using these operators A of P and B dot B of P, from this canonical commutation relation among the fields, you can derive what the commutation relations among this A and A dagger, B and B dagger should be, and that turns out to be this. And when you see this one, then you say, aha, these are the creation-addition operators of particles. So you set up the vacuum state as usual. Which is annihilated by generation operator. Then you can create one A particle. You can also create one B particle. That's in one particle state. You can create two A particles. You can create two B particles. And you can create also one each if you like. And so on and so forth. Now you got your Hilbert space. And also that you have the Lagrangian, and from the Lagrangian you can define the Hamiltonian, which is pi dot plus pi dagger minus L. Because I have two independent variables of pi and pi dagger. And if you plug the Lagrangian into this and use this mode expansion in A and A dagger, this turns into the form that looks familiar. And if you insist on writing constants, a 0-point energy, I get half each, so I get 1 here. So this turns out to be the Hamiltonian. Then interpretation is very simple. Once you create a particle of momentum p, that state has energy given by the square root of p squared c plus c squared plus m squared c to the fourth. And that's exactly the relativistic particle we wanted. But one strange thing is that in addition to a one particle species we wanted, it came out with two particle species, which apparently have the same mass, because energy for both A and B particles is given by p squared c squared plus m squared c to the fourth of the same mass m, which was already in the Lagrangian somewhere, which I erased, sorry. But if you remember, the Lagrangian looked like action was dt dq del mu pi dagger del mu phi minus m squared c squared over a squared pi dagger phi. So this m was a parameter in Lagrangian, so there's only single m, so that m apparently describes the mass for both A and B particles. Yes?
So there's two indistinguishable spin zero particles here?
Yeah, this is spin zero particle, but there are actually two particles in it.
How do we know there's two? We can't distinguish between them.
Well, they are different operators, and A and B commute, so that means they are orthogonal. So because A and B commute, even when you have dagger on this, when you have a particle state created for A, and when you have another particle state created by B, and if you take the inner product of them, I take dagger of this, right? That's the inner product. But because they commute, B can act directly on the vacuum state, and it vanishes. So these states are orthogonal to each other, so they can't be the same state.
Experimentally, how do we know there's two separate types of particles?
Yeah, so that's something I will come now,
Okay.
but any questions about what we have just done? Yes, Jackie?
The second term, pi, the pi dagger in the Hamiltonian?
This? Yeah.
Yeah, could you say
Pi,
that
phi,
again?
and pi dagger are done. Pi dagger done. Sorry, I forgot this thought. Is
That's
that?
just to make a remission?
Well, that's one way to say it, but another way to say is that because we have the complex field phi and phi dagger can be treated as independent variables. So then you have to introduce canonical conjugate momentum for each one of them. And when you go for the Lagrange Hamiltonian, you need to do this Legendre transformation for both of them. And that turns out to be also Hermitian, so it sort of does a double duty. Okay? Any other questions here? Okay, now comes the Sudan's question. So what's going on here? Why do you have the same, there are two different particles with the same mass? So what we have done so far is trying to write down the relativistic quantum field theory. This is the simplest things we could come up with because we wanted to get Klein-Gordon equation based on the inspiration of the first failed attempt of building relativistic quantum mechanics. And once we wrote down this relativistic QFT, now we have this weird fact that there seems to be two particle species of the same mass. And that's the first time we see the idea of antimatter. For example, we know there are spin zero particles in nature called pions. And this is now known to be made of quark, up quark, and anti-up quark. Up quark has charge 2/3, very strange, but that's true. Down quark has charge -1/3, so its antiparticle has charge +1/3. If you add them together, that's charge +1, so this particle exists. At the same time, there is also the antiparticle of this particle, called pi minus. They have opposite charges, plus and minus, but has the same mass of about 140 MeV/s. This way. And this is the first time we see this phenomenon, that once you have a particle species, there can be its antiparticle species. That's described by this A and B here for the Klein-Gordon field. So that's now the prediction when you try to make QFT relativistic. Somehow this marriage of the relativity and quantum physics led to the relativistic QFT, which now gives you a prediction that the particle has its antiparticle counterpart, namely antimatter. And indeed, this is actually not just for the Klein-Gordon field, but generalized to any particle species. And Berkeley is the birthplace of antiproton up in the lab. What they have done is to smash a beam of proton on a target. Bunch of particles come out here. But when you do so, among these bunch of particles that was produced, they discovered the antiproton inside. And antiproton was sent into a photographic film because antiproton is charged compared to proton of charge +1, antiproton has charge -1. When the charged particle is sent into a photographic film, it keeps ionizing the material inside the film, so you actually see this particle traveling into it after you develop the film. You can see the track. And once it actually stops in the end, it looks something like this. It's called a star event. And what happened here is that antiproton came in, hits the proton, particle and antiparticle would annihilate with each other. It disappears, completely disappears from our universe. But of course there's an energy. And that energy now turns back into particles like pi plus and pi minus. So particle and antiparticle can annihilate with each other, and particle and antiparticle can be created with each other. So this is a process called pair creation. This is a process called pair annihilation. And that's how, the two Berkeley scientists, Segre and Chamberlain, received Nobel Prize for this discovery that proton also has an antimatter counterpart named antiproton. So what we are seeing here is the first example of that, okay?
Yeah, so from the very beginning of we wrote down phi.
Huh?
We already introduced the mixing of operators for A and B. At that time, do we know that it's of the same species?
Well, we didn't know that, but we worked out and found that they have the same mass. And if two different particles have the same mass, that sounds like too much of an accident. But now we see the reason. Because they are particle-antiparticle pair, they should have the same mass. And that turns out to be the prediction of relativistic QFT. Namely that relativistic QFT predicts every particle has antiparticle of same mass. So here I'm talking about one example, which is described by this Klein-Gordon field, which is spin 0. And example here is the particle called pion, and it's charged, so there is a pi plus and pi minus, and they are particle-antiparticle pair and have the same mass. So this is first example of this general statement about relativistic QFT, which applies to every particle in the universe. Yes?
So if we add interaction terms to the Hamiltonian, is that enough to see the annihilation, or do we have to couple it to another field?
You have to couple it to another field. So for example, when you have this coupling, suppose you have field phi and another field capital phi. And you can write down relativistic field theories for them. And do the same thing for capital phi. But this may have different mass, so let me make this capital M. Then you can also introduce an interaction term like this. So capital phi dagger, capital phi, little phi dagger, little phi. And inside this, you have creation and annihilation operators for particles and antiparticles for little phi field. In capital phi, you have creation and annihilation operators for particle-antiparticle of, let's say, capital A and capital B. And if you do the mode expansion, you find a term that looks like this, for instance. And once you have a term like this one, what it can do is to let these phi particles A and B come in. They are particle-antiparticle pair. And so you annihilate them. But then you can create A and B out of that. So this term in the Lagrange then describes this process of pair annihilation for the particle capital phi and pair creation of particle little phi, which you can observe in experiments. And indeed, when you do the scattering of pi plus pi minus, they can annihilate and produce particles like k plus k minus. That's yet another Klein-Gordon field, spin 0 particle. They have very different masses. I told you this 140. This one is 498, if I remember correctly. And if these guys are slow, then total energy here is 280 MeV. That's not enough to create them. But if you send the pi plus pi minuses with enough energy using particle accelerators, then once you exceed the total energy in the initial state of twice the KO mass, then you can observe this process, and people do. Okay.
Yeah, and for one question on saying that we recognize the anti-particle pair because they have the same mass, we just pulled out the term M, but if we were to verify that the two particles that we have the same mass,
Right.
then we should let M and M prime, and then, but I
But you
don't
can't
see-
do that because it came from the same term in the Lagrangian.
It came from.
Same term in the Lagrangian. There's only a single parameter in the Lagrangian, M. And that M, after doing the Legendre transformation to write out the Hamiltonian, turned into M in that expression in the Hamiltonian. So you can't make them different.
So if I were to understand this, we have to go back to how did we actually know
Yeah,
that?
so for example, if you have two different fields, then you can write two different terms with two different masses. And indeed, you can have this kind of process, that one type of particle can now turn into another type of particle by pair annihilation and pair creation, so that's possible. But you're still constrained in a way that pi minus and pi minus have the same mass because that came from the same term in the Lagrangian, M. K plus and K minus have the same mass because their masses came out from this term in the Lagrangian with capital M. So you can't change the fact that these guys have the same mass, these guys have the same mass. Different types of particles can have different masses, but particle and antiparticle always have the same mass. Yes, that.
But we chose to add that term which annihilates them together. How do we know it's canonically true that they're gonna like be?
Well, at least this is experimentally observed. So from the data, now you have to write a term like this. So that's something you know experimentally. Okay? Any other questions?
I'm still confused about the mode extension at the very beginning. So you add
I erased, I guess. Yeah.
You add A and B
Uh-huh.
when you do the mode extension.
Uh-huh.
But when we did the vector potentials in electromagnetic fields, we only have the A operator, right?
You know, that's an excellent question too. So let me write this again. By X. So Terry's question is, why do they have to be different? And that's because phi field, we started out, is a complex field. So here, we are not assuming n phi is Hermitian. That's what's meant by complex. And this is the first thing we tried, because initially, we wanted to write a Schrödinger equation. And Schrödinger equation has a complex wave function, so we sort of naturally assume that this is complex, and we never question that on the way. But if it's complex, but still use this A and B the same, you find this happens to be Hermitian. And that's not what we assumed initially. But now that you ask, you can have Klein-Gordon field, which is Hermitian, which is called, for obvious reason, real Klein-Gordon field. In this case, your Lagrangian has slightly different normalization with a factor of half. I would say just for technical reason. Now I'm not using complex conjugation anywhere because phi by itself is real. And if I quantize this theory instead, which is different from what we have done for complex Klein-Gordon field, now you have to make sure that phi is real. And for real Klein-Gordon field, then this A has to be matched by its Hermitian conjugate. Then I have to make this A dagger, which means that particle and antiparticle are the same for a real Klein-Gordon field. And that particle also exists in addition to pi plus and pi minus, which are particle-antiparticle pair. There's another particle called pi naught. And this is real Klein-Gordon field, and therefore it's antiparticle of its own, while pi plus and pi minus are definitely different particles because they have different electrical charges, but they are particle-antiparticle pair, so they have the same masses. So you can have real Klein-Gordon field, which is antiparticle for its own, or complex Klein-Gordon field, where particle and antiparticle are distinct because of some opposite charges of some kind. And the photon is a real field, vector potential is a real field. So we didn't question this, but in retrospect, photon is similar to pi naught, where photon is the same as antiphoton, where you don't have any distinction between photon and antiphoton, because it doesn't have electric charge, for instance. There's no distinction between them. But for charged particles, there is definitely a distinction between particle and antiparticle because they have opposite electrical charges. Yes, Sam?
Why for like the real Klein-Gordon field could you not just have two pions?
Yeah, so that's a good question. And so what I wanted to talk about now, before I run out of time, is that once you have a Lagrangian, then you can derive various the Newton's theorem, conserved charges. And when you have a Lagrangian with a complex Klein-Gordon field, you have a symmetry of changing the phase of phi, because that's cancelled by change of the phase in phi dagger. And once you have a symmetry, there's an associated conservation law. And that conservation law turns out to be the conservation of electrical charge. And you can also work out that the electrical charge, the conserved quantity, turns out to be real. AP dagger AP minus BP dagger BP. So whenever you create A particle, you gain charge 1. Whenever you create B particle, you get charge -1. So that's the way you can see that they have opposite charges. But at the same time, this is the conserved quantity because it comes out from the symmetry of the Lagrangian as a conserved quantity. So that's how you see a conserved quantity, which is the opposite for A and B particles, hence matter, antimatter. But once you identify A and B, which you have to do for real Klein-Gordon field, then this cancels. So charge is identically 0. And indeed, pi naught doesn't have an electric charge. So that's how everything works out consistently. So thanks for the question, Sam. Okay, I have to stop here. Any further questions? Okay, now you have seen antimatter.